Hello there, and welcome to our journey through the mysteries of interstellar space. Tonight, we will explore everything we know about the most enigmatic visitors ever to grace our solar system, the interstellar objects that have fundamentally changed our understanding of what lies between the stars. We are going to discover the complete story of these cosmic wanderers that have traveled unimaginable distances to reach our cosmic neighborhood. From the first mysterious cigar-shaped object that tumbled through our solar system like nothing we had ever seen before, to the latest discoveries that continue to challenge our assumptions about interstellar travelers. These are not just asteroids or comets from our solar system, but true wanderers from the depths of space, each carrying unique secrets from stellar nurseries and planetary systems that existed long before our Earth was born. We will explore every detail we've uncovered about these ancient travelers, their strange behaviors, their puzzling trajectories, their mysterious compositions, and what their brief visits have taught us about the cosmos beyond our solar system. Before we begin this comprehensive exploration, I would love to know where you are joining us tonight. Perhaps you are in a quiet room, maybe lying back with your eyes closed, ready to absorb the full story of these cosmic mysteries. No matter where you are, we share this moment together, floating on our small planet through the vastness of space, witnesses to some of the most extraordinary discoveries in modern astronomy. If you find these kinds of detailed scientific explorations fascinating, I would be grateful if you could subscribe or like this program. It helps this signal reach other curious minds who enjoy diving deep into the most intriguing phenomena in our universe. Take a moment now to settle in. Let your thoughts expand to encompass the vast scales of space and time we're about to explore. Our story begins on the 19th day of October in 2017, when Hawaiian astronomer Robert Wyrick noticed something unusual moving across the night sky. The object appeared as nothing more than a faint dot of light through the Pan-STARRS telescope at Haleakala Observatory. Yet this tiny speck would soon reshape our understanding of the cosmos and become the first confirmed visitor from beyond our solar system, an object that would eventually bear the Hawaiian name Oumuamua, meaning messenger from afar, arriving first. High above the Pacific Ocean, the telescope's sophisticated cameras captured images of stars scattered like distant diamonds against the black velvet of space. Among these familiar celestial landmarks, one point of light behaved differently. While stars remained fixed in their positions, this particular dot shifted steadily westward at more than 6 degrees per day. Such rapid motion immediately caught the attention of the automated detection systems designed to spot asteroids and comets threatening Earth. The discovery unfolded during the quiet hours when most of the world slept peacefully. Astronomers who study near-Earth objects often work through the night, their dedication protecting our planet from cosmic hazards. These scientific guardians scan the heavens methodically, searching for any wandering rocks that might pose danger to Earth. On this particular October evening, their vigilance revealed something far more extraordinary than anyone anticipated. Initial observations suggested the object followed a highly unusual trajectory. Most asteroids and comets in our solar system travel along predictable elliptical paths around the Sun. These orbits reflect billions of years of gravitational sculpting by our star and the giant planets. However, this new object displayed characteristics that defied such familiar patterns. Its path appeared hyperbolic, meaning it would visit our solar system once and then continue into the vast emptiness between stars. The astronomical community responded with remarkable speed and coordination. Within hours of the announcement, telescopes around the world turned their attention toward this mysterious visitor. Observatories in Chile, Spain, and across the United States joined the effort to gather as much information as possible before the object disappeared forever into interstellar space. Time worked against them as the visitor traveled at extraordinary velocity and grew dimmer with each passing day. Scientists initially classified the object as a comet, assigning it the designation C/2017 U1. This classification reflected their expectation that any interstellar visitor would likely consist of ice and dust, similar to the frozen wanderers that occasionally grace our skies with spectacular tails. Comets originate in the cold outer regions of planetary systems, where water and other substances remain frozen for billions of years. When these icy bodies approach a star, solar heating causes them to develop characteristic glowing halos and streaming tails. However, the very deep observations revealed something puzzling. Despite passing closer to the Sun than Mercury's orbit, the object showed no signs of cometary activity. No glowing coma surrounded it. No streaming tail followed behind. The absence of these expected features forced astronomers to reconsider their initial assessment. Within days, they reclassified the object as an asteroid, changing its designation to A/2017 U1. The visitor's lack of visible outgassing surprised researchers who had anticipated seeing typical comet behavior. Solar radiation should have heated any surface ice to the point of sublimation, creating the distinctive fuzzy appearance that characterizes active comets. Yet even the most sensitive instruments detected no hint of gas or dust emission. This suggested the object's surface consisted primarily of rocky or metallic material rather than the expected ice and organic compounds. As observations accumulated, astronomers realized they had encountered something unprecedented in the history of astronomy. The object's hyperbolic trajectory confirmed it originated outside our solar system, making it the first interstellar visitor ever detected passing through our cosmic neighborhood. This milestone discovery earned the object a new classification system entirely, becoming one I/2017 U1, where the I designated as an interstellar object. The scientific community chose to honor the discoverers by adopting their suggested name for the object. They called it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. This poetic designation captured both the object's distant origins and its historic significance as humanity's first confirmed encounter with matter from another star system. The name reflected the cultural heritage of the observatory where the discovery occurred, acknowledging the indigenous wisdom that views the sky as part of a greater interconnected universe. Follow-up observations revealed additional mysteries that deepened scientific interest in Oumuamua. The object's brightness varied dramatically over time, dimming and brightening in a regular pattern that suggested rapid rotation. These variations exceeded anything previously observed in solar system objects, indicating either an extremely elongated shape or unusual surface properties. Astronomers had never encountered a natural body with such extreme characteristics. Spectroscopic analysis provided insights into the visitor's composition and history. The object appeared reddish in color, similar to many asteroids and comet nuclei in the outer solar system. This coloration likely resulted from billions of years of cosmic ray bombardment during its journey through interstellar space. High-energy particles gradually alter surface chemistry, creating complex organic compounds that absorb blue light while reflecting longer wavelengths toward the red end of the spectrum. The discovery's timing proved fortuitous for modern astronomy. Advanced sky survey programs like Pan-STARRS had only recently achieved the sensitivity necessary to detect such faint, fast-moving objects. Earlier generations of telescopes would likely have missed Oumuamua entirely, leaving humanity unaware that visitors from other star systems regularly pass through our solar system. The detection demonstrated how technological progress continues expanding our ability to explore and understand the universe. Research teams worldwide scrambled to observe Oumuamua before it faded beyond the reach of even the largest telescopes. The Hubble Space Telescope tracked the object's position with extraordinary precision, while ground-based observatories measured its color and brightness variations. Each night brought new data that helped scientists piece together the visitor's properties and probable history. The object's rapid departure created a sense of urgency rarely experienced in astronomical research. Unlike planets, stars, or galaxies that remain available for extended study, Oumuamua offered only a brief window for investigation. Astronomers had to work quickly and efficiently to extract maximum scientific value from this unprecedented opportunity. The experience taught valuable lessons about preparing for future interstellar visitors, which surveys like Pan-STARRS and the upcoming Legacy Survey of Space and Time are expected to detect regularly. By early November 2017, Oumuamua had already passed beyond Mars's orbit and continued accelerating away from the Sun. Its incredible speed of nearly 90,000 miles per hour ensured it would escape our solar system entirely, never to return. The brief encounter lasted only a few months, but the scientific impact would resonate for years to come. Humanity had received its first tangible sample of matter from beyond our cosmic neighborhood, opening new avenues for understanding planetary formation and the distribution of material throughout the galaxy. The discovery of Oumuamua marked a watershed moment in astronomy, comparable to the first detection of exoplanets orbiting other stars. For the first time, scientists could study an object that formed in a distant planetary system under conditions that might differ significantly from those that shaped our own solar system. This visitor carried information about stellar environments, planetary formation processes, and the mechanisms that scatter debris across interstellar space. Each measurement provided clues about the cosmic processes that connect star systems throughout our galaxy. Scientists believe that most objects in space follow familiar geometric patterns. Asteroids typically resemble irregular potatoes, while planets tend towards spherical forms shaped by their own gravity. Comets often appear as loose collections of ice and rock, rounded by countless impacts and thermal cycles. Yet Oumuamua challenged every assumption astronomers held about natural celestial bodies, displaying proportions so extreme that they seem to defy the normal processes that sculpt cosmic objects. The first hints of Oumuamua's unusual form came through measurements of its varying brightness. As the object rotated, it grew brighter and dimmer in a regular cycle that repeated approximately every 7 1/3 hours. This pattern suggested rotation, but the magnitude of brightness changes exceeded anything previously recorded in our solar system. The object's light output varied by more than 2.5 magnitudes, meaning it appeared more than 10 times brighter at maximum than at minimum. Such dramatic variations in reflected sunlight indicated an extraordinarily elongated shape. When Oumuamua presented its long side toward Earth-based telescopes, it reflected significantly more light than when viewed end-on. Astronomers had observed similar but much smaller variations in some asteroids, particularly tiny near-Earth objects observed at high phase angles. However, none exhibited the extreme ratios displayed by this interstellar visitor. Detailed analysis of the brightness patterns revealed that Oumuamua possessed the most elongated shape ever confirmed in a natural celestial object. Initial calculations suggested a length-to-width ratio of at least 5:1, with some models indicating proportions as extreme as 10:1. For comparison, the most elongated asteroids known in our solar system rarely exceed 3:1 ratios, making Oumuamua truly exceptional among cosmic bodies. The mathematical modeling required to determine shape from brightness variations involves complex calculations accounting for rotation geometry, viewing angle, and surface properties. Astronomers must consider how light scatters from different materials under various conditions. Oumuamua's rapid rotation and changing distance from Earth complicated these analyses, requiring sophisticated computer models to extract reliable shape parameters from the observational data. Computer simulations explored various possible configurations that could produce the observed brightness patterns. These models considered both cigar-shaped prolate ellipsoids and flattened pancake-like oblate forms. Interestingly, both geometries could potentially explain the dramatic light variations depending on the viewing angle and rotational orientation. Recent research suggests that a pancake shape might better match the complete dataset of observations. The tumbling nature of Oumuamua's rotation added another layer of complexity to shape determination. Unlike most asteroids that spin smoothly around a single axis, Oumuamua appeared to wobble chaotically through space. This non-principal axis rotation, or tumbling motion, created intricate brightness patterns that varied subtly from one rotational cycle to the next. Such complex dynamics made it extremely challenging to derive definitive shape parameters. Evidence for tumbling came from careful analysis of brightness measurements taken over multiple nights. No single rotation period could adequately explain all the observed variations. Instead, the data suggested multiple overlapping periodicities consistent with an object precessing around different axes simultaneously. This tumbling state likely originated from some violent event in Oumuamua's past, perhaps a collision or tidal disruption that imparted complex angular momentum. The physical mechanisms that could create such extreme elongation in a natural object remain subjects of scientific debate. Standard formation processes in planetary systems typically produce more rounded bodies through accretion and gravitational settling. Collision fragments might achieve modest elongation, but rarely approach the proportions exhibited by Oumuamua. Some researchers propose that tidal forces during close stellar encounters could stretch and reshape objects into such unusual configurations. Alternative explanations focus on erosion and sublimation processes during the object's long journey through interstellar space. If Oumuamua originally possessed a more conventional shape, cosmic ray bombardment and micrometeorite impacts over millions of years might gradually sculpt it into its current form. However, these processes typically create more irregular cratered surfaces rather than smooth, elongated shapes. The pancake hypothesis emerged from detailed reanalysis of photometric data using improved models of surface scattering properties. This interpretation suggests Oumuamua measures approximately 147 by 144 by 24 meters, resembling a flattened disc rather than a cigar. Such proportions might result from rotational flattening if the object once spun much more rapidly, or from compression during a violent formation event. Surface composition analysis provided additional constraints on Oumuamua's shape and formation history. Spectroscopic observations revealed a uniformly reddish coloration consistent with organic-rich materials that have undergone extensive space weathering. The lack of significant spectral features suggested a relatively homogeneous surface composition, which might be expected from an object that experienced severe reshaping or erosion. The absence of detected compositional variations across Oumuamua's surface supported models of violent formation mechanisms. If the object formed through tidal disruption or high-velocity collision, the resulting thermal processing could create a relatively uniform surface layer. Alternatively, prolonged cosmic ray exposure during interstellar travel might gradually homogenize surface materials, erasing evidence of original compositional diversity. Comparisons with other elongated objects in our solar system provided context for understanding Oumuamua's extreme proportions. The asteroid Itokawa, visited by Japan's Hayabusa spacecraft, displays a roughly 2-to-1 length ratio and appears to consist of two components held together by weak gravitational attraction. Contact binary asteroids like Erikoth in the Kuiper Belt also show elongated forms, but none approach Oumuamua's extreme aspect ratio. The discovery of such an unusually shaped object raised questions about the population of interstellar visitors and their formation mechanisms. If Oumuamua represents a typical example of ejected planetary material, it suggests that violent processes capable of creating extremely elongated objects operate commonly in other star systems. Alternatively, Oumuamua might be an exceptional case, with most interstellar objects possessing more conventional proportions. Size estimates for Oumuamua depend critically on assumptions about surface reflectivity, or albedo. With an assumed albedo similar to dark asteroids, the object measures roughly 100 to 400 meters in its longest dimension. If the surface reflects light more efficiently, the actual size would be correspondingly smaller. These uncertainties affect mass estimates and thus theories about the object's origin and evolution. The relationship between Oumuamua's shape and its mysterious acceleration remains an active area of research. Some scientists propose that outgassing from the elongated object's surface could provide sufficient thrust to explain the observed non-gravitational forces. The large surface area associated with extreme elongation might enhance such effects, making them detectable even when invisible to telescopes. Future observations of additional interstellar visitors will help determine whether Oumuamua's extreme shape represents a common characteristic or a rare anomaly. The recently discovered interstellar comet Borisov displayed more conventional proportions, suggesting significant diversity exists among objects ejected from other planetary systems. Each new detection provides additional data points for understanding the processes that create and shape interstellar wanderers. The legacy of Oumuamua's unusual form extends beyond its specific characteristics to broader questions about planetary formation and evolution. Its extreme elongation challenges existing models of how solid bodies form and survive in space environments. The object serves as a natural laboratory for testing theories about tidal disruption, collision dynamics, and erosion processes that operate throughout the galaxy. As Oumuamua continues its journey into deep space, it carries with it the mystery of its remarkable shape. The brief encounter provided tantalizing glimpses of formation processes operating in distant stellar systems, while raising new questions about the diversity of objects wandering between the stars. This enigmatic visitor demonstrated that the universe contains surprises that stretch our understanding of what natural processes can create. Something subtle yet profound was occurring as Oumuamua journeyed through our solar system. The object traveled faster than gravitational forces alone could explain, accelerating away from the sun by a small but measurable amount that puzzled astronomers worldwide. This deviation from predicted orbital mechanics represented one of the most intriguing aspects of humanity's first confirmed interstellar visitor. Precise tracking of celestial objects requires extraordinary attention to detail and mathematical accuracy. When astronomers plot the trajectory of an asteroid or comet, they account for gravitational influences from the sun, planets, and even the largest moons. These calculations typically predict positions with remarkable precision, allowing spacecraft to navigate across billions of kilometers and arrive at their destinations within minutes of scheduled encounters. However, Oumuamua refused to follow the carefully calculated path that should have governed its motion through our solar system. High-precision measurements from the Hubble Space Telescope revealed systematic deviations from the expected orbit. By early May 2018, when the object reached Jupiter's distance from the Sun, it had strayed approximately 100,000 kilometers from its predicted position. This discrepancy might seem small when considered against the vast scales of interplanetary space. The deviation equaled roughly 1/4 of the distance between Earth and the Moon, a tiny fraction of Oumuamua's total journey. Yet for astronomers, accustomed to predicting celestial motions with extraordinary accuracy, such a significant departure from theoretical expectations demanded careful investigation and explanation. The magnitude of Oumuamua's acceleration provided important clues about its likely cause. During the period when it passed closest to the Sun, the object gained approximately 17 meters per second of additional velocity beyond what gravitational forces could explain. This boost occurred gradually over several months rather than as a sudden impulse, suggesting some continuous physical process rather than a single dramatic event. Several mechanisms could potentially account for such non-gravitational acceleration. Outgassing from cometary nuclei represents the most familiar example of how celestial objects can deviate from purely gravitational trajectories. As comets approach the Sun and heat up, subsurface ice sublimates into gas that jets away from the surface, creating rocket-like thrust that alters orbital motion. This phenomenon occurs regularly among comets in our solar system. Yet Oumuamua displayed none of the visual signatures typically associated with cometary outgassing, Sensitive observations using large ground-based and space-based telescopes detected no trace of the glowing coma or streaming tail that characterize active comets. The absence of these features suggested that any gas emission must be extremely subtle, invisible to even sophisticated detection methods. Research teams proposed various explanations for how Oumuamua could experience acceleration without producing detectable gas clouds. Perhaps the object released hydrogen molecules too sparse to create visible effects, or maybe it vented gas uniformly across its entire surface rather than through discrete jets. Alternative theories suggested that solar radiation pressure acting on the object's unusual shape might generate sufficient force to explain the observed acceleration. The tumbling nature of Oumuamua's rotation added complexity to understanding its motion through space. Unlike objects that spin steadily around a single axis, Oumuamua appeared to wobble chaotically, processing through multiple rotational states simultaneously. This complex motion pattern, known as non-principal axis rotation or tumbling, created intricate variations in how the object presented itself to solar radiation and any escaping gases. Analysis of rotational data revealed that Oumuamua completed one tumbling cycle approximately every 7 1/3 hours. However, the precise period varied slightly over time, and the brightness patterns showed subtle differences from one rotation to the next. These variations indicated that multiple factors influenced the object's spin state, possibly including outgassing forces, tidal effects, and internal structural changes. The tumbling motion itself provided evidence of violent events in Oumuamua's history. Objects achieve such complex rotational states through catastrophic collisions, tidal disruption during close stellar encounters, or other energetic processes that impart chaotic angular momentum. Once established, tumbling motion persists for extremely long periods, potentially billions of years, making it a lasting signature of past trauma. The animals to model Oumuamua's acceleration required sophisticated computer simulations incorporating multiple physical effects. Researchers had to account for solar radiation pressure, possible outgassing gravitational perturbations from planets, and the complex geometry associated with the object's unusual shape and tumbling motion. These calculations demanded enormous computational resources and careful validation against observational data. The most comprehensive studies concluded that gentle outgassing provided the most plausible explanation for Oumuamua's mysterious acceleration. This interpretation suggested that the object retained small amounts of volatile materials beneath its surface, possibly water ice or other compounds that could sublimate when heated by solar radiation. The resulting gas jets would be too faint to detect directly, but sufficient to produce measurable orbital changes. Recent theoretical work has focused on hydrogen outgassing as a particularly attractive explanation for the observed acceleration. Cosmic ray bombardment during Oumuamua's long interstellar journey could gradually convert water ice into molecular hydrogen trapped within the object's interior. Solar heating would then drive this hydrogen to escape, creating thrust without producing visible emissions or significant rotational torques. The hydrogen hypothesis elegantly addresses several puzzling aspects of Oumuamua's behavior. Molecular hydrogen is nearly impossible to observe directly, explaining the absence of detectable gas emissions. It also provides relatively gentle uniform thrust that wouldn't dramatically alter the object's rotation state. Furthermore, cosmic ray processing represents a natural consequence of prolonged interstellar travel, making this mechanism broadly applicable to similar visitors. Alternative explanations continue to receive scientific attention, though most face significant theoretical or observational challenges. Solar radiation pressure alone appears insufficient to explain the magnitude of acceleration, especially given Oumuamua's likely composition and surface properties. More exotic proposals involving artificial origins or novel physical effects lack supporting evidence and require extraordinary claims that exceed available data. The debate over Oumuamua's acceleration highlights the challenges inherent in studying interstellar objects. These visitors provide only brief opportunities for observation before disappearing forever into deep space. Astronomers must extract maximum information from limited data, often leading to competing interpretations that cannot be definitively resolved. Each proposed explanation must balance theoretical plausibility against observational constraints. Understanding Oumuamua's motion has broader implications for recognizing and characterizing future interstellar visitors. The subtle acceleration signature might serve as an important diagnostic tool for distinguishing genuine interstellar objects from conventional solar system bodies with unusual orbits. Improved detection methods and more sensitive telescopes should enable better characterization of such effects in subsequently discovered objects. The mystery surrounding Oumuamua's acceleration also demonstrates how astronomical discoveries can challenge existing theoretical frameworks. Scientists have developed sophisticated models for predicting celestial motions over billions of years, yet this single object revealed gaps in our understanding of how small bodies behave in space environments. Such surprises drive scientific progress by highlighting phenomena that require deeper investigation. As Oumuamua continues its eternal journey between the stars, it carries the secrets of its unusual motion into the cosmic depths. The brief encounter provided valuable insights into the complex physics governing small celestial bodies, while raising new questions about the diversity of objects wandering throughout our galaxy. Future interstellar visitors will undoubtedly present their own unique characteristics, gradually building our understanding of these cosmic messengers. What stories do colors tell about journeys across the cosmos? The light reflected from Oumuamua's surface carried information about billions of years spent wandering between the stars, revealing chemical processes that occur during the longest voyages imaginable. This reddish hue provided scientists with their first direct glimpse into how interstellar space transforms matter over geological timescales. Spectroscopy represents one of astronomy's most powerful tools for understanding distant objects. When starlight reflects off an asteroid or planet, different materials absorb and reflect specific wavelengths and characteristic patterns. These spectral fingerprints allow astronomers to identify surface compositions without physically visiting the object. Iron oxides create reddish colors, while water ice appears blue-white, and organic compounds often produce darker, more neutral tones. The first spectroscopic observations of Oumuamua revealed a distinctly reddish coloration similar to many objects found in the outer regions of our solar system. This deep red hue suggested the presence of complex organic compounds that had undergone extensive processing by cosmic radiation. Such coloration typically develops over millions or billions of years as high-energy particles gradually alter surface chemistry through radiolysis and other processes. Detailed analysis of Oumuamua's reflected light showed remarkably uniform properties across its entire surface. Unlike many asteroids that display significant spectral variations between different regions, this interstellar visitor appeared homogeneous in both color and reflectivity. Such uniformity suggested either a recent resurfacing event that exposed fresh material, or alternatively, such thorough processing that original compositional differences had been completely erased. The absence of significant absorption features in Oumuamua's spectrum puzzled researchers expecting to identify specific minerals or ices. Most rocky bodies display diagnostic features corresponding to common silicate minerals, while icy objects show characteristic water absorption bands. Oumuamua's relatively featureless spectrum suggested either an unusual composition or extensive alteration that had masked original diagnostic signatures. Comparative studies with objects in our solar system provided context for interpreting Oumuamua's spectral properties. The reddish coloration most closely resembled that of D-type asteroids, found primarily in the outer asteroid belt, as well as many Kuiper belt objects and comet nuclei. These populations share similar organic-rich compositions that darken and redden through prolonged exposure to cosmic radiation and solar wind particles. The degree of reddening observed in Oumuamua implied an extended period of space, weathering far exceeding typical timescales in our solar system, while objects orbiting near Earth experience relatively rapid alteration due to intense solar radiation. Those in the outer solar system weather more slowly. Interstellar space presents an entirely different environment, with lower radiation fluxes, but exposure times measured in millions or billions of years. Computer models of space weathering processes helped scientists estimate how long Oumuamua might have wandered between the stars. The observed color index suggested exposure times of at least several 100 million years, though uncertainties in radiation environment and original composition made precise age determinations challenging. Some models indicated possible ages of billions of years, implying formation during the early epochs of galactic evolution. The uniform spectral properties across Oumuamua's surface raised questions about its formation mechanism and subsequent evolution. Objects that form through accretion typically display compositional heterogeneity, reflecting different materials incorporated during growth. However, violent formation processes like tidal disruption or high-velocity impacts can create more homogeneous bodies through thermal processing and mechanical mixing. Research teams investigated whether Oumuamua's spectral characteristics could provide clues about its system of origin. Different stellar environments produce distinct radiation conditions that might leave recognizable signatures in space-weathered surfaces. Young, massive stars generate intense ultraviolet radiation that could create different alteration products than the gentler environments around older, cooler stars like our Sun. The measured albedo, or reflectivity, of Oumuamua provided additional constraints on surface composition and texture, with approximately 10% of incident sunlight reflected back to space. The object appeared relatively dark, similar to carbonaceous asteroids and comet nuclei in our solar system. This low reflectivity suggested a surface rich in dark organic compounds and possibly fine-grained dust that efficiently absorbs light. Thermal infrared observations attempted to measure heat emission from Oumuamua's surface, which would provide independent estimates of size and thermal properties. However, the object's faintness and rapid motion made such measurements extremely challenging. The few successful detections suggested surface temperatures consistent with rocky or metallic composition rather than ice-rich materials that would sublime more readily. The lack of detected emission lines in Oumuamua's spectrum indicated minimal outgassing activity during its passage through our solar system. Active comets typically display characteristic emission features from excited gas molecules in their comas, particularly carbon compounds, water vapor, and simple organic molecules. The absence of such features supported the interpretation that any gas emission from Oumuamua was too subtle to detect directly. Polarimetric measurements, which analyze the polarization properties of reflected light, provided additional insights into surface texture and composition. These observations suggested a surface roughness similar to that of asteroids rather than the smoother textures characteristic of fresh cometary ices. The polarization properties supported models of an aged processed surface covered with fine particulate material. The spectral energy distribution, from ultraviolet through infrared wavelengths, painted a picture of an object unlike anything previously studied in detail. The smooth, red-sloped spectrum resembled laboratory measurements of organic compounds subjected to prolonged irradiation. Such materials, known as tholins, form naturally when simple organic molecules are exposed to high-energy radiation over extended periods. Some researchers proposed that Oumuamua's surface composition might preserve information about conditions in its birth environment. If the object formed in the outer regions of a distant planetary system, its original composition could reflect the inventory of volatile and organic materials available during planet formation. Cosmic ray processing would then gradually modify this primordial signature while preserving some original characteristics. The investigation of Oumuamua's colors and spectra demonstrated both the power and limitations of remote sensing techniques. While these methods revealed important clues about surface composition and evolutionary history, many questions remained unanswerable without direct sampling or more detailed observations. The brief encounter highlighted the need for improved instruments and observational strategies for future interstellar visitors. Alternative interpretations of the spectral data continued to emerge as researchers refined their analysis techniques and theoretical models. Some studies suggested that unusual geometric effects associated with Oumuamua's extreme shape could influence its observed colors and brightness variations. Others explored whether surface heterogeneity on scales smaller than telescopic resolution might create apparent spectral uniformity. The colors of interstellar space, as revealed through Oumuamua's weathered surface, provided humanity's first direct sample of matter processed in environments completely different from our solar system. This reddish messenger carried chemical signatures of billion-year journeys through regions where different radiation fields, temperatures, and particle densities shaped its evolution. Each photon reflected from its surface told part of a story spanning cosmic time. As Oumuamua faded beyond the reach of even the most sensitive telescopes, it took with it the detailed secrets of its composition and origin. However, the spectroscopic legacy of this brief encounter established important baselines for interpreting future interstellar visitors. The techniques developed and refined during these observations would prove invaluable for characterizing the next cosmic messenger that ventures into our solar neighborhood. The tale, written in Oumuamua's colors, speaks of patience, endurance, and transformation on scales that dwarf human experience. Through countless eons of wandering, this small world absorbed the accumulated history of galactic evolution, preserving it in the altered chemistry of its ancient surface. In studying these colors, humanity glimpsed the deep processes that connect stellar systems across the vast expanses of space. Throughout the history of astronomy, scientists have created categories to organize the diverse objects they discover in space. Planets, asteroids, comets, and moons each occupy distinct classifications based on their orbits, compositions, and behaviors. Yet Oumuamua defied every existing category, forcing astronomers to invent entirely new terminology for humanity's first confirmed interstellar visitor. The initial moments of any astronomical discovery involve rapid assessment and preliminary classification. Automated survey systems like Pan-STARRS generate thousands of detections each night, most proving to be known asteroids following predictable paths. When unusual motion patterns trigger alerts, human experts examine the data more carefully to determine whether the object represents something genuinely novel or simply a familiar body observed under uncommon circumstances. Robert Warwick's first analysis of the moving object suggested cometary characteristics. The hyperbolic trajectory implied the body originated from the outer solar system, where most comets spend billions of years in deep freeze. Such objects occasionally fall sunward when gravitational perturbations from passing stars or giant molecular clouds disturb their distant orbits. Following established protocols, astronomers assigned the designation C/2017 U1, indicating a suspected comet discovered in late October. However, continued observations revealed behavior inconsistent with typical cometary activity. As Oumuamua approached the Sun and experienced increasing solar heating, sensitive telescopes detected no signs of the gas and dust emission that characterizes active comets. Even small comets usually develop detectable comas when they venture inside Jupiter's orbit. Yet this object remains stubbornly inactive despite reaching closer distances than Mercury. The absence of cometary activity prompted reassessment of the object's nature and appropriate classification. Asteroids, unlike comets, consist primarily of rocky or metallic materials that remain stable when exposed to solar radiation. These objects rarely develop visible atmospheres, making them appear as star-like points of light, even when observed through powerful telescopes. Within days of the original announcement, astronomers reclassified the object as A/2017 U1. Yet even the asteroid designation felt inadequate for describing Oumuamua's unique characteristics. Asteroids in our solar system follow elliptical orbits that keep them gravitationally bound to the Sun over billions of years. This interstellar interloper followed a dramatically different path, approaching from the direction of the constellation Lyra and departing toward Pegasus with sufficient velocity to escape solar gravity entirely. No previously known asteroid exhibited such extreme orbital properties. The recognition that Oumuamua originated beyond our solar system created an unprecedented classification challenge. Existing nomenclature systems assumed all natural objects belong to our Sun's gravitational family, with designations reflecting discovery circumstances and orbital characteristics within that framework. This visitor required fundamentally different treatment, acknowledging its exotic origin and temporary presence in our cosmic neighborhood. International astronomical organizations moved quickly to establish new classification standards for interstellar objects. The Minor Planet Center, responsible for cataloging small solar system bodies, worked with the International Astronomical Union to create appropriate designations. They settled on a new category, denoted by the letter I, transforming Oumuamua's designation to one I/2017 U1, where the numeral 1 indicated it was the first confirmed interstellar object. This groundbreaking classification established precedent for future discoveries of similar objects. The system anticipates regular detection of interstellar visitors as sky surveys improve their sensitivity and coverage. Each new object would receive sequential numbering, reflecting the order of discovery, creating a permanent catalog of matter sampled from other stellar systems. Within 2 years, the system proved its utility with the discovery of the interstellar comet 2I/Borisov. The physical properties that defied easy classification extended beyond orbital mechanics to encompass size, shape, and composition characteristics. Oumuamua's extreme elongation exceeded typical asteroid proportions by factors of 3 to 5, while its uniform reddish coloration suggested surface processing unlike anything observed in conventional solar system objects. These attributes challenged existing models of how natural bodies form and evolve in space environments. Spectroscopic analysis revealed additional complications for classification efforts. The object's featureless spectrum lacked diagnostic absorption lines that typically identify specific mineral compositions in asteroids. Similarly, the absence of emission features ruled out active outgassing processes characteristic of comets. Oumuamua seemed to occupy an intermediate category, displaying properties of both object types while fully matching neither. The discovery sparked scientific debate about appropriate terminology for describing interstellar objects with ambiguous characteristics. Some researchers favored broad categories that emphasized orbital properties over physical attributes, arguing that origin provides the most fundamental distinguishing characteristic. Others preferred classifications based on composition and activity level, maintaining consistency with existing asteroid and comet categories while acknowledging interstellar origins. Theoretical considerations added complexity to classification discussions. Computer models of planetary system evolution predict that both rocky and icy materials should be ejected into interstellar space through gravitational interactions with giant planets. This suggests future interstellar visitors will display the full range of compositions observed in our own solar system's small body populations, plus exotic types that form under different stellar environments. The tumbling rotation state provided another unusual characteristic requiring consideration in classification schemes. While some asteroids exhibit non-principal axis rotation following collisions or other disruptions, the extreme nature of Oumuamua's tumbling motion suggested particularly violent origins. This complex dynamical state might serve as a diagnostic signature for objects ejected through catastrophic processes rather than gentler planetary scattering mechanisms. Size estimates for Oumuamua placed it within the range of small asteroids and large meteoroids, but uncertainties in surface reflectivity made precise determinations challenging The object's elongated shape, complicated size measurements based on brightness observations, as different viewing angles presented varying amounts of surface area. These ambiguities highlighted the need for more sophisticated observational techniques for characterizing future interstellar visitors. The brief observational window available for studying Oumuamua emphasized the importance of rapid classification and characterization protocols. Unlike permanent solar system objects that remain available for extended investigation, interstellar visitors offer only limited opportunities for detailed study before disappearing forever. Astronomers must quickly recognize unusual objects and mobilize appropriate observational resources to maximize scientific return. Development of automated classification systems represents an active area of research motivated by Oumuamua's discovery. Machine learning algorithms trained on large datasets of known asteroids and comets could potentially identify unusual objects in real time, triggering immediate follow-up observations. Such systems might prove essential as next-generation sky surveys detect hundreds or thousands of interstellar visitors over the coming decades. The legacy of Oumuamua's classification challenges extends beyond astronomical terminology to broader questions about how we organize and understand the natural world. This single object forced expansion of conceptual frameworks that had seemed adequate for describing all possible celestial phenomena. The experience demonstrated how scientific discovery often requires not just new observations, but new ways of thinking about observation results. Educational institutions worldwide updated their curricula to incorporate lessons learned from humanity's first interstellar visitor. Textbooks added new sections on interstellar objects, while planetarium shows explained the classification puzzle to public audiences fascinated by this cosmic messenger. The discovery provided a compelling example of how science adapts its organizational structures to accommodate unexpected findings. Museums and science centers faced similar challenges in presenting Oumuamua to visitors accustomed to traditional solar system exhibits. Display designers had to explain not just the object's unusual properties, but also the process by which scientists created new categories to accommodate unprecedented discoveries. These educational efforts helped broader audiences appreciate both the object itself and the dynamic nature of scientific classification. As astronomical surveys continue detecting additional interstellar objects, the classification framework established for Oumuamua will undoubtedly require further refinement and expansion. Each new visitor will test existing categories and potentially demand new subcategories, reflecting the diversity of matter ejected from other stellar systems. The puzzle begun by humanity's first interstellar visitor will continue evolving as our cosmic perspective expands. In the vastness between stars, countless objects drift silently through space, each carrying the story of its birth and the cosmic events that launched it on an interstellar journey. Oumuamua arrived at our solar system bearing clues about its origins, yet deciphering these hints required astronomers to peer backward through millions or perhaps billions of years of galactic history. The trajectory analysis provided the first important clues about where Oumuamua might have originated. By carefully measuring its path through our solar system and accounting for gravitational influences from the sun and planets, astronomers could extrapolate backward to determine its approach direction. The object appeared to arrive from the general direction of the bright star Vega in the constellation Lyra, suggesting a possible connection to that stellar neighborhood. However, the apparent association with Vega proved more complex than initial calculations suggested. Stars move through the galaxy on their own orbital paths around the galactic center, and their positions change significantly over the timescales required for interstellar travel. When astronomers accounted for stellar motion over the past several 100,000 years, they found that Vega occupied a very different position when Oumuamua would have departed its system of origin. The challenge of tracing interstellar trajectories highlights the dynamic nature of our galactic neighborhood. Stars orbit the galactic center at different velocities depending on their distances and masses, creating a complex dance of stellar motions that reshuffles cosmic geography over millions of years. An object ejected from one stellar system might appear to arrive from an entirely different direction after accounting for these motions. Theoretical models of planetary system evolution provide frameworks for understanding how objects like Oumuamua might be ejected into interstellar space. During the early phases of planet formation, gravitational interactions between growing planets often destabilize smaller bodies, flinging them out of their birth systems. Computer simulations suggest that most planetary systems eject large quantities of material during these chaotic formative periods. The efficiency of this ejection process depends on the architecture of each planetary system. Systems with massive planets in eccentric orbits prove particularly effective at scattering smaller bodies, while more stable configurations retain most of their original material. Statistical studies of known exoplanet systems suggest enormous diversity in planetary arrangements, implying equally diverse populations of ejected interstellar objects. Recent research has focused on specific mechanisms that could create objects with Oumuamua's unusual characteristics. The extreme elongation and tumbling rotation suggest formation through violent processes rather than gradual accretion. One leading hypothesis proposes that tidal forces during close encounters with stars could stretch and reshape planetary bodies, creating the extreme proportions observed in this interstellar visitor. The tidal disruption scenario envisions a regionally more conventional asteroid or planetesimal that ventured too close to its parent star or another massive object. The resulting gravitational stresses would exceed the body's structural strength, stretching it into an elongated shape while imparting the complex rotational motion observed today. Computer models demonstrate that such encounters could produce objects with the required geometric and dynamical properties. Alternative formation theories explore whether Oumuamua might represent a fragment of a larger body destroyed through catastrophic collision. High-velocity impacts between asteroids or planets can produce debris with a wide range of sizes and shapes. The most elongated fragments from such events might resemble Oumuamua's extreme proportions, while the violence of the collision could explain the object's tumbling rotation state. The nitrogen ice hypothesis represents a fundamentally different approach to understanding Oumuamua's origins. This theory suggests the object consists of frozen nitrogen, similar to the surface compositions of Pluto and Triton. According to this model, a fragment of an exo-Pluto's surface could explain both the unusual shape and the mysterious acceleration observed during the object's solar passage. Nitrogen sublimation would occur gradually as Oumuamua approached the Sun, creating gentle thrust without producing visible gas clouds detectable by telescopes. The proposed mechanism could account for the observed acceleration while explaining the absence of typical cometary activity. Furthermore, prolonged sublimation over millions of years might sculpt the object into its current elongated form. Chemical evolution during interstellar travel adds another layer of complexity to origin theories. Cosmic ray bombardment gradually alters surface compositions through nuclear reactions and molecular dissociation. Objects that spent billions of years in interstellar space might bear little resemblance to their original compositions, making it challenging to identify their formation environments based solely on observed properties. The reddish coloration observed in Oumuamua provides important constraints on origin scenarios. Similar colors characterize many objects in the outer solar system, where organic compounds undergo gradual processing by radiation and charged particles. This suggests formation in a cold environment similar to the outer regions of planetary systems, where volatile materials remain stable over geological timescales. Studies of stellar populations in our galactic neighborhood attempt to identify candidate parent systems for Oumuamua and future interstellar visitors. Young star-forming regions contain embedded stellar clusters where close encounters between developing planetary systems might be common. Alternatively, older stellar populations might have had more time to eject material through long-term dynamical evolution. The age and metallicity of potential parent stars provide additional clues about formation conditions. Stars that formed during different epochs of galactic evolution had access to different inventories of heavy elements, which would influence the compositions of their planetary systems. Objects ejected from very old metal-poor stars might display compositional signatures distinct from those formed around younger, metal-rich hosts. Recent work has explored whether Oumuamua might originate from disrupted planetary systems around dying stars. As stars evolve beyond the main sequence, they can destabilize or completely destroy their planetary systems through mass loss and changing gravitational fields. The resulting debris could include objects with unusual properties that reflect the extreme conditions present during stellar evolution. Binary star systems present additional opportunities for ejecting planetary material through gravitational interactions. Close approaches between binary components can destabilize planetary orbits, particularly when the stellar masses or orbital parameters change over time. Such systems might produce interstellar objects with different characteristics than those ejected from single-star systems, like our own. The discovery of multiple interstellar objects will eventually provide statistical constraints on origin mechanisms and parent stellar populations. Each new visitor carries information about formation processes operating in different stellar environments. Comparative studies of these objects should reveal whether Oumuamua represents a typical example or an unusual case among interstellar wanderers. Isotopic measurements, if ever obtained from interstellar objects, would provide definitive evidence about their stellar origins. Different stellar environments produce characteristic isotopic ratios that serve as fingerprints of formation conditions. Future space missions capable of analyzing samples from interstellar visitors could revolutionize our understanding of planetary formation throughout the galaxy. The question of Oumuamua's origins ultimately connects to broader issues in astronomy and planetary science. Understanding how planetary systems form, evolve, and exchange material helps address fundamental questions about the prevalence of habitable worlds and the potential for life to spread between star systems. Each interstellar visitor provides a piece of this cosmic puzzle. Advanced theoretical models continue refining predictions about the properties and frequency of interstellar objects based on different formation scenarios. These models guide observational strategies for detecting and characterizing future visitors, while helping interpret the limited data available from brief encounters. The interplay between theory and observation drives progress in understanding these cosmic messengers. As Oumuamua continues its journey into the depths of space, it carries with it the unresolved mysteries of its origin. The object serves as a reminder that our solar system exists within a dynamic galactic environment where matter regularly travels between stellar neighborhoods. Future discoveries will gradually illuminate the processes that create and disperse these interstellar wanderers throughout our galaxy. The search for Oumuamua's birthplace represents more than academic curiosity about a single unusual object. It reflects humanity's deeper quest to understand our place in the cosmos and the connections that link stellar systems across vast distances. Through studying these visitors from afar, we glimpse the broader context within which our own world formed and evolved. Deep within stellar systems, gravitational forces usually maintain orderly arrangements where planets circle their stars in stable orbits that persist for billions of years. Yet occasionally, cosmic catastrophes disrupt this peaceful harmony, creating conditions so extreme that solid bodies stretch and deform like soft clay. Such events might explain how Oumuamua acquired its remarkable elongated shape through the violent physics of tidal disruption. Tidal forces arise whenever different parts of an object experience varying gravitational pulls. Earth's ocean tides demonstrate this principle on a familiar scale, as the moon's gravity tugs more strongly on water facing our satellite than on water on the opposite side of our planet. For small objects like asteroids, tidal effects remain negligible under normal circumstances. However, during close encounters with massive bodies, these forces can become overwhelmingly powerful. Computer simulations reveal the dramatic consequences when a rocky asteroid ventures too close to a star or massive planet. As the object approaches, differential gravitational forces begin stretching it along the direction pointing toward the massive body. Initially, the asteroid's structural strength resists this deformation, but continued approach increases the tidal stress until the material can no longer maintain its original shape. The critical distance where tidal forces overcome structural integrity depends on both the mass of the disrupting body and the composition of the approaching object. Dense, rocky asteroids can venture closer to massive objects before experiencing disruption, while loose collections of rubble succumb to tidal forces at greater distances. For stellar encounters, this Roche limit typically lies within a few stellar radii, placing disrupting objects perilously close to stellar surfaces. Research teams have modeled scenarios where planetary bodies approach various types of stars under different circumstances. Young, massive stars generate intense radiation fields that could heat and soften approaching objects, making them more susceptible to tidal deformation. Alternatively, encounters with white dwarf stars, despite their compact size, could produce extreme tidal gradients due to their concentrated masses. The elongation process during tidal encounters proceeds through several distinct phases. Initial deformation creates a slightly stretched ellipsoid as the object responds to increasing gravitational stress. Continued approach transforms this into a highly elongated prolate spheroid resembling an elongated football. Eventually, the tidal forces may exceed the object's gravitational self-attraction entirely, causing it to fragment into multiple pieces. For objects that survive the encounter while retaining structural integrity, the stretching process leaves permanent deformation. The originally spherical or irregular asteroid emerges from the encounter with dramatically altered proportions, potentially approaching the extreme 10-to-1 axis ratios inferred for Oumuamua. Simultaneously, the gravitational torques during closest approach impart complex rotational motion that could persist for billions of years. The tumbling rotation observed in Oumuamua provides strong evidence supporting tidal disruption scenarios. During close stellar encounters, gravitational forces act asymmetrically on elongated objects, creating torques that spin them in complicated ways. This non-principal axis rotation, once established, remains stable indefinitely in the absence of additional external forces, preserving evidence of the violent encounter that created it. Heat generation during tidal deformation represents another important aspect of these encounters. The mechanical stresses involved in stretching solid rock generate internal friction that converts gravitational energy into thermal energy. For severe deformation events, this heating could temporarily melt surface materials, creating the relatively smooth, homogeneous surface properties observed in Oumuamua. Thermal processing during tidal encounters might also explain the uniform spectral characteristics that puzzled astronomers studying this interstellar visitor. Melting and resolidification would erase original compositional variations, creating surfaces with consistent properties across the entire object. Subsequent cooling and cosmic ray processing during interstellar travel would gradually develop the reddish coloration observed today. The survival probability for objects undergoing tidal encounters depends on their internal structure and composition. Solid, monolithic bodies resist disruption more effectively than loose aggregates held together by weak gravitational forces. However, even coherent objects have limits to the stress they can withstand, and sufficiently close approaches will fragment any natural material regardless of its strength. Statistical studies of stellar encounters in dense stellar environments help estimate how frequently tidal disruption events might occur. Young star clusters contain hundreds or thousands of stars within relatively small volumes, increasing the probability of close approaches between stellar systems. These regions might serve as factories for producing tidally elongated objects that subsequently escape into interstellar space. Binary star systems present particularly rich environments for tidal disruption events. The gravitational dynamics of close binary pairs create complex tidal fields that could stretch and reshape planetary bodies in their vicinity. Evolution of binary systems through stellar mass loss or orbital decay might trigger encounters that disrupt previously stable planetary configurations. The efficiency of tidal elongation mechanisms depends critically on the encounter geometry and relative velocities involved. Head-on collisions produce different deformation patterns than glancing encounters, while the approach speed determines how much time is available for stretching before the objects separate. These parameters influence both the final axis ratios and the rotational properties of surviving fragments. Advanced numerical simulations incorporate realistic material properties and equation of state models to predict the outcomes of tidal encounters More accurately, these calculations must account for the complex rheology of rock and ice under extreme conditions, including temperature-dependent softening and strain rate effects. The results help identify which encounter scenarios could produce objects with Oumuamua's observed characteristics. Observational evidence for tidal disruption events has emerged from studies of other astronomical phenomena. Stellar tidal streams around galaxies contain stars torn from disrupted globular clusters, demonstrating that such processes operate on various scales throughout the universe. Similarly, planetary debris disks around white dwarf stars likely contain material from tidally destroyed planets. The chemical composition of tidally processed objects might differ from conventional asteroids due to thermal and mechanical processing during the encounter. High temperatures could drive off volatile materials, alter mineral structures, or promote chemical reactions that change surface properties. These modifications would contribute to the unusual spectral characteristics observed in interstellar visitors. Future space missions capable of intercepting interstellar objects could potentially test tidal disruption theories through detailed compositional analysis, measurements of isotopic ratios, mineral assemblages, and microstructures would reveal whether objects experienced the high temperature, high stress conditions associated with tidal encounters. Such data would provide definitive tests of formation mechanisms. The implications of tidal disruption scenarios extend beyond explaining individual objects like Oumuamua to broader questions about planetary system evolution. If tidal encounters commonly reshape planetary bodies, they might influence the size distributions and physical properties of small body populations throughout the galaxy. Understanding these processes could illuminate the violent history hidden within seemingly peaceful stellar neighborhoods. Alternative mechanisms for creating elongated objects include catastrophic collisions between planetary bodies and gradual erosion processes during interstellar travel. Each formation pathway would leave distinctive signatures in object properties, compositions, and rotational states. Comparative studies of multiple interstellar visitors should eventually distinguish between these competing theories. The tidal disruption hypothesis also makes predictions about the frequency and characteristics of future interstellar visitors. If such encounters commonly occur in dense stellar environments, surveys should detect regular streams of elongated objects with similar properties to Oumuamua. The absence or presence of such populations would provide important tests of the theory. As our understanding of stellar dynamics and planetary formation continues evolving, the tidal disruption scenario for Oumuamua's origin remains one of several plausible explanations for this remarkable object. The theory elegantly connects the visitor's unusual shape, complex rotation, and surface properties to well-understood gravitational physics operating under extreme conditions. The story written in Oumuamua's elongated form speaks of cosmic violence on scales that dwarf terrestrial experience. Through studying this deformed messenger, astronomers glimpse the catastrophic processes that periodically reshape planetary systems, scattering their contents across the galaxy like seeds blown on cosmic winds. How many worlds exist beyond our solar system, and what processes shape their formation and evolution? Oumuamua represents far more than a curious astronomical oddity. It constitutes our first direct sample of matter from another stellar system, providing unprecedented insights into planetary formation processes operating throughout our galaxy. Each measurement of this interstellar messenger illuminates the diverse environments where planets and smaller bodies develop around distant stars. The discovery that interstellar objects regularly visit our solar system implies a vast population of such wanderers drifting through the galaxy. Statistical analyses based on Oumuamua's detection rate suggest that trillions of similar objects currently populate the space between stars, representing material ejected from countless planetary systems over billions of years. This enormous inventory reflects the efficiency with which gravitational interactions scatter solid bodies during planetary formation. Computer models of planetary system evolution predict that ejection processes operate most vigorously during the early phases of planet formation. Young stellar systems contain massive disks of gas and dust, where planetary embryos grow through accretion and collision. As these bodies reach larger sizes, their gravitational interactions become increasingly chaotic, ultimately resulting in configurations where a few large planets dominate, while countless smaller objects get flung into interstellar space. The efficiency of this scattering process depends critically on the masses and orbital arrangements of the forming planets. Systems that develop massive planets in eccentric orbits prove particularly effective at ejecting smaller bodies, while more circular, widely spaced planetary configurations retain larger fractions of their original solid material. The diversity observed in known exoplanet systems suggests equally diverse populations of ejected interstellar objects. Studies of our own solar system's formation provide context for understanding these ejection mechanisms. During the late heavy bombardment, approximately 4 billion years ago, gravitational perturbations from the giant planets destabilized populations of asteroids and comets, sending many into the inner solar system while ejecting others entirely. Similar processes likely operate in all planetary systems, though with varying intensities depending on planetary masses and configurations. The compositional properties inferred for Oumuamua offer glimpses into the inventory of materials available during planet formation in its birth system. The reddish, organic-rich surface suggests formation in the cold outer regions of a planetary system, where volatile compounds remain stable over geological timescales. This implies the presence of a substantial disk of solid material extending well beyond the orbit of any central star. The extreme elongation and tumbling rotation of Oumuamua indicate formation through violent processes rather than gentle accretion, whether created through tidal disruption, catastrophic collision, or other energetic mechanisms. Such properties reflect the chaotic dynamics that characterize planetary formation. The survival of such a delicate object suggests that violent events can create durable structures under appropriate circumstances. Size distribution analyses of interstellar object populations provide constraints on the masses and numbers of solid bodies in typical planetary systems. Oumuamua's dimensions place it within the size range of large asteroids or small moonlets, suggesting that planetary systems commonly produce substantial numbers of kilometer-scale objects. Scaling relationships derived from our solar system predict even larger populations of smaller bodies. The detection rate of interstellar visitors depends on both their intrinsic abundance and the size distribution of the population. Large objects like Oumuamua are easier to detect, but presumably less numerous than smaller bodies. Current survey capabilities primarily sample the largest members of the interstellar population, missing vast numbers of smaller objects that could provide additional insights into planetary formation processes. Chemical evolution during interstellar transit complicates efforts to reconstruct original formation conditions from observed properties. Cosmic ray bombardment gradually alters surface compositions over millions of years, potentially erasing signatures of birth environments. However, subsurface materials might preserve more pristine records of original compositions, awaiting future sampling missions capable of drilling into interstellar visitors. The trajectory characteristics of interstellar objects provide information about their ejection velocities and timing. Oumuamua's approach velocity of approximately 26 kilometers per second relative to the local standard of rest suggests ejection from a planetary system with relatively modest gravitational perturbations. Higher velocity objects might originate from more violent encounters or disruptions of tighter planetary configurations. Theoretical models predict that different types of planetary systems should produce interstellar objects with distinctive characteristics. Systems dominated by gas giants might eject primarily icy bodies from their outer regions, while systems with massive terrestrial planets could scatter more rocky material. Future observations of diverse interstellar visitors should reveal correlations between object properties and formation environments. The study of interstellar objects also illuminates the role of stellar evolution in planetary system dynamics. As stars age and change their masses or luminosities, they can destabilize previously stable planetary configurations. Red giant evolution, in particular, might trigger massive ejection events as stellar mass loss reduces gravitational binding throughout the system. Binary star systems present additional complexities for planetary formation and subsequent ejection processes. Gravitational interactions between stellar companions can pump planetary eccentricities, leading to enhanced scattering rates. Close binary pairs might completely prevent stable planet formation, while wider binaries could produce planetary systems with unusual architectures and enhanced ejection probabilities. The frequency of interstellar objects provides statistical constraints on planetary formation efficiency throughout the galaxy. If most stars form planetary systems that subsequently eject significant fractions of their solid material, the observed abundance of interstellar visitors becomes understandable. Conversely, if planetary formation typically produces stable configurations with minimal ejection, alternative sources for the interstellar population would be required. Comparative planetology benefits enormously from direct sampling of materials formed under different stellar conditions. Variations in stellar mass, metallicity, and radiation environment should influence the compositions and properties of planetary building blocks. Interstellar objects provide natural experiments for testing how these factors affect planetary formation processes. The isotopic compositions of interstellar objects, when eventually measured, will provide definitive fingerprints of their stellar origins. Different generations of stars produce characteristic isotopic signatures, reflecting their formation epochs and nuclear processing histories. Such measurements could reveal whether interstellar visitors primarily originate from young or old stellar populations. Future space missions designed to intercept and sample interstellar objects could revolutionize our understanding of planetary formation throughout the galaxy. Direct analysis of pristine materials from other stellar systems would provide unprecedented insights into the diversity of planetary building blocks and formation processes. Such missions represent high-priority targets for advancing comparative planetology. The implications of Oumuamua's discovery extend beyond academic astronomy to fundamental questions about the prevalence and characteristics of planetary systems. If interstellar objects commonly exchange between stellar systems, they might facilitate the spread of organic compounds or even primitive life forms throughout the galaxy. This panspermia hypothesis remains speculative, but worthy of continued investigation. The discovery of regular interstellar visitors also suggests that our solar system continuously receives samples from throughout our galactic neighborhood. While most such objects remain too small for detection, they nevertheless contribute to the ongoing evolution of our planetary system through accretion and bombardment. This process connects Earth's evolution to broader galactic processes. Advanced theoretical models continue refining predictions about interstellar object populations based on improved understanding of planetary formation mechanisms. These models guide observational strategies for detecting and characterizing future visitors, while helping interpret the limited data available from brief encounters. The interplay between theory and observation drives progress in understanding these cosmic samples. Educational and public outreach efforts increasingly emphasize the connections between interstellar objects and planetary formation processes. Understanding how planets form around other stars has become central to astrobiology and the search for potentially habitable worlds. Interstellar visitors provide tangible links between our solar system and the broader population of planetary systems throughout the galaxy. As astronomical surveys improve their sensitivity and coverage, they will detect interstellar objects with increasing frequency. Each new discovery will add to our understanding of planetary formation diversity, while testing theoretical predictions about ejection mechanisms and population characteristics. The small sample begun with Oumuamua will gradually expand into a comprehensive database of interstellar materials. The legacy of humanity's first confirmed interstellar visitor extends far beyond its specific characteristics to encompass broader insights into planetary system evolution. Through studying this cosmic messenger and its successors, astronomers are constructing a new field of galactic comparative planetology that illuminates the processes shaping worlds throughout our cosmic neighborhood. Astronomers worldwide now scan the heavens with renewed purpose, searching for additional visitors from beyond our solar system. The discovery of Oumuamua transformed what had been theoretical speculation into observational reality, proving that interstellar objects regularly traverse our cosmic neighborhood. This confirmation launched an intensive effort to detect, track, and study these elusive cosmic messengers before they disappear forever into the depths of space. Advanced sky survey programs represent the front line of this search effort. Projects like the Catalina Sky Survey, Linear, and Pan-STARRS systematically photograph large areas of sky each night, comparing new images with previous observations to identify moving objects. These automated systems process enormous volumes of data, flagging unusual motion patterns that might indicate interstellar visitors among the thousands of conventional asteroids and comets detected monthly. The success of these surveys depends critically on their ability to distinguish interstellar objects from solar system bodies with unusual orbits. Conventional comets from the Oort cloud can approach from any direction and display hyperbolic trajectories similar to true interstellar visitors. Only through careful orbital analysis can astronomers determine whether an object originated within our solar system or arrived from interstellar space. Within 2 years of Oumuamua's discovery, this detective work paid off with the identification of a second confirmed interstellar visitor. In August 2019, amateur astronomer Gennady Borisov detected a comet that subsequent analysis revealed to follow a clearly hyperbolic orbit originating beyond our solar system. This object, designated 2I/Borisov, became the second member of the growing catalog of interstellar visitors. Unlike its predecessor, 2I/Borisov displayed obviously cometary characteristics throughout its passage near the Sun. The object developed a prominent coma and tail as solar heating sublimated ice from its nucleus, creating the familiar appearance associated with conventional comets. This visible activity made it easier to study than the enigmatic Oumuamua, providing valuable insights into the composition and behavior of interstellar objects. Spectroscopic analysis of 2I/Borisov revealed compositions remarkably similar to comets native to our solar system. The object's nucleus appeared to contain familiar mixtures of water ice, carbon dioxide, and organic compounds in proportions consistent with formation in cold outer planetary regions. This similarity suggested that basic planetary formation processes operate consistently across different stellar systems. The discovery of 2 such different interstellar objects within a short time frame hinted at the diversity awaiting detection in this new population. Oumuamua's rocky, elongated characteristics contrasted sharply with Borisov's conventional cometary appearance, suggesting that interstellar space harbors objects representing the full range of compositions and formation mechanisms operating in planetary systems throughout the galaxy. Statistical analyses based on these early detections predicted discovery rates for future interstellar visitors. Extrapolating from the limited sample suggested that existing survey programs should detect several such objects annually as their sensitivity and sky coverage continue improving. These predictions motivated investments in enhanced detection capabilities and rapid response observational strategies. The development of specialized protocols for interstellar object characterization became a priority for the astronomical community. Unlike permanent solar system objects that remain available for extended study, interstellar visitors offer only brief windows for detailed observation before fading beyond telescopic reach. Maximizing scientific return requires coordinated international efforts and pre-planned observational campaigns. Next-generation survey telescopes promise dramatic improvements in interstellar object detection capabilities. The Vera Rubin Observatory's Legacy Survey of Space and Time will photograph the entire visible sky every few nights with unprecedented depth and precision. This comprehensive monitoring should detect interstellar visitors much sooner after their arrival, providing extended opportunities for detailed study. Advanced data processing techniques increasingly rely on machine learning algorithms trained to recognize the subtle signatures of interstellar objects among vast data sets. These automated classification systems can process observational data much faster than human analysts, potentially identifying unusual objects in near real time and triggering immediate follow-up observations while targets remain bright enough for detailed study. The prospect of intercepting interstellar visitors with spacecraft missions has captured scientific imagination worldwide, unlike conventional solar system targets that follow predictable orbits. Interstellar objects present unique challenges for mission design due to their high velocities and limited warning times. Successful interception would require either pre-positioned spacecraft or revolutionary propulsion technologies. Project Lyra represents one ambitious proposal for chasing down Oumuamua using Jupiter gravity assists and advanced propulsion systems. While the original visitor has already traveled too far for practical interception, similar mission concepts could be adapted for future discoveries detected earlier in their approach. Such missions would provide unprecedented opportunities for detailed in situ analysis of interstellar materials. The scientific community has also explored concepts for rapid deployment missions using small lightweight spacecraft that could be launched quickly after interstellar object detection. These CubeSat swarms might carry simplified instrumentation packages capable of basic compositional analysis during high-speed flyby encounters. While limited in scope, such missions could complement ground-based observations with unique measurements impossible from Earth. Theoretical predictions about interstellar object populations continue evolving as more objects are discovered and characterized. Early models based solely on Oumuamua suggested predominantly rocky compositions, while the discovery of the more conventional comet Borisov indicated greater compositional diversity. Future detections will refine these population models and improve predictions about discovery rates and object characteristics. The search for interstellar objects benefits from international cooperation and data sharing agreements that maximize global observational coverage. Objects detected by one survey program receive immediate follow-up observations from telescopes worldwide, creating comprehensive data sets that would be impossible for any single institution to obtain. This collaborative approach has become the standard for studying these fleeting cosmic visitors. Amateur astronomers play increasingly important roles in interstellar object discovery and characterization. The detection of 2I/Borisov by a dedicated amateur demonstrates how modern technology has democratized astronomical discovery. Sophisticated cameras and analysis software now enable individual enthusiasts to contribute meaningfully to cutting-edge research programs. Educational institutions worldwide have incorporated interstellar object searches into their curricula, training new generations of astronomers in the techniques required for detecting and studying these elusive targets. Student research projects focusing on data analysis and object characterization provide valuable workforce development while contributing to scientific understanding of the interstellar population. Public interest in interstellar objects has motivated citizen science programs that engage broader audiences in the search effort. Projects like Galaxy Zoo and similar platforms allow volunteers to examine astronomical images and identify unusual objects that might escape automated detection algorithms. These crowdsourcing approaches leverage human pattern recognition capabilities to complement computer-based analysis. The implications of regular interstellar visitor detection extend beyond astronomy to broader questions about planetary system evolution and astrobiology. If organic compounds commonly survive interstellar transport. These objects might facilitate chemical evolution or even biological exchange between stellar systems. Understanding their compositions and survival mechanisms becomes crucial for assessing such possibilities. Future space-based telescopes will dramatically enhance interstellar object detection capabilities by providing continuous sky monitoring without atmospheric interference. Projects like NEO-Surveyor focus primarily on potentially hazardous asteroids, but will undoubtedly discover additional interstellar visitors as secondary science targets. Space-based observations also enable studies at wavelengths blocked by Earth's atmosphere. The development of real-time alert systems ensures rapid dissemination of interstellar object discoveries to the global astronomical community. When surveys detect potentially interesting targets, automated systems immediately notify observatories worldwide, enabling coordinated follow-up campaigns within hours of initial detection. This infrastructure proves essential for maximizing scientific return from brief encounter opportunities. As the catalog of known interstellar objects gradually expands, comparative studies will reveal patterns and correlations that illuminate their origins and evolution. Early results suggest fascinating diversity in composition, structure, and dynamics that reflects the varied environments where these objects formed. Each new discovery adds crucial data points to our understanding of planetary formation throughout the galaxy. The hunt for interstellar visitors has transformed from speculative theory to routine observational astronomy within just a few years. What began with the surprising discovery of Oumuamua has evolved into a systematic search program that regularly samples matter from throughout our galactic neighborhood. This ongoing effort continues expanding our perspective on the interconnected nature of planetary systems and the dynamic processes that shape cosmic evolution. Consider the scale of a single small object traveling through space, no larger than a city block, yet capable of revolutionizing humanity's understanding of the cosmos. Oumuamua's brief passage through our solar system lasted only months, but its scientific and cultural impact will resonate for generations. This solitary messenger from beyond transformed theoretical possibilities into observational realities, opening new fields of research and fundamentally expanding our cosmic perspective. The scientific legacy of Oumuamua extends far beyond its specific characteristics to encompass entirely new approaches to studying the universe. Before its discovery, interstellar objects existed only in theoretical models and computer simulations. Astronomers speculated about their properties and abundance, but lacked direct observational evidence. The confirmation that such objects regularly visit our solar system validated decades of theoretical work while revealing unexpected complexities. Research programs worldwide redirected resources toward interstellar object studies. Following the discovery, universities established new research groups focused on these cosmic visitors, while funding agencies created special programs to support related investigations. The interdisciplinary nature of interstellar object research brought together astronomers, planetary scientists, astrobiologists, and engineers in collaborative efforts that transcended traditional academic boundaries. The technological innovations spurred by Oumuamua's discovery continue influencing astronomical instrumentation and data analysis techniques. Survey telescopes adopted enhanced algorithms for detecting fast-moving objects, while spectroscopic instruments developed improved capabilities for studying faint, rapidly changing targets. These advances benefit numerous areas of astronomy beyond interstellar object research. Educational institutions at all levels incorporated lessons from Oumuamua into their curricula, recognizing the discovery's value for teaching scientific methodology and cosmic perspective. Elementary schools use the visitor's story to introduce concepts of solar systems and space exploration, while graduate programs developed specialized courses in interstellar object astronomy. The discovery provided a compelling example of how scientific understanding evolves through observation and analysis. Public engagement with astronomy reached new heights following widespread media coverage of humanity's first confirmed interstellar visitor. Planetariums worldwide developed special programs about Oumuamua, while science museums created exhibits exploring the implications of its discovery. The object's mysterious properties and exotic origin captured public imagination in ways that traditional astronomical discoveries often struggle to achieve. The cultural impact of Oumuamua extended beyond scientific circles to influence art, literature, and popular culture. Science fiction authors incorporated interstellar visitors into their narratives, while artists drew inspiration from the object's unusual characteristics. The discovery reinforced themes of cosmic connectivity and the dynamic nature of space that resonate throughout human culture. Philosophical implications of regular interstellar visitors challenge traditional views of planetary systems as isolated entities. The recognition that matter regularly travels between stellar systems suggests a more interconnected galaxy where local environments reflect broader cosmic processes. This perspective influences how we understand Earth's place in the universe and the potential for life to spread between worlds. The discovery established important precedents for international cooperation in studying transient astronomical phenomena. The coordinated global response to Oumuamua's detection demonstrated how quickly the scientific community could mobilize resources for studying unexpected discoveries. This collaboration model now serves as a template for investigating future cosmic visitors and other time-sensitive astronomical events. Funding priorities in astronomy shifted to accommodate the new field of interstellar object research. Space agencies began planning missions to intercept future visitors, while ground-based observatories allocated telescope time for follow-up observations of candidate objects. The potential scientific return from studying pristine samples of extraterrestrial matter justified significant investments in detection and characterization capabilities. The debate surrounding Oumuamua's unusual properties stimulated healthy scientific discourse about the nature of evidence and the process of theory development. Competing explanations for the object's characteristics led to productive exchanges that refined understanding of planetary formation, stellar evolution, and interstellar transport mechanisms. This scientific debate exemplified how unexpected discoveries drive progress in understanding natural phenomena. Advanced computational methods developed for modeling Oumuamua's properties found applications in other areas of astronomy and planetary science. Techniques for analyzing light curves from tumbling objects improved studies of asteroid rotation states, while thermal models developed for interstellar visitors enhanced understanding of cometary activity. These methodological advances continue benefiting diverse research programs. The discovery highlighted the importance of serendipity in scientific research, while demonstrating how prepared minds can capitalize on unexpected opportunities. Oumuamua was discovered through routine asteroid surveys rather than dedicated searches for interstellar objects. This emphasizes how maintaining broad observational capabilities can lead to transformative discoveries in unexpected areas. International policy discussions about planetary defense incorporated lessons learned from Oumuamua's discovery. While this particular visitor posed no threat to Earth, its detection demonstrated the need for enhanced capabilities to track and characterize potentially hazardous objects approaching from unexpected directions. These considerations influence ongoing efforts to protect our planet from cosmic impacts. The economic implications of interstellar object research extend beyond immediate scientific benefits to encompass potential technological spin-offs and industrial applications. Advanced propulsion concepts developed for intercepting fast-moving visitors might enable more efficient spacecraft missions throughout the solar system. Similarly, techniques for rapid object characterization could benefit commercial space ventures and resource utilization efforts. Future space exploration missions increasingly consider the possibility of encountering interstellar materials during their operations. Spacecraft instrumentation now includes capabilities for detecting and analyzing unexpected objects that might cross mission trajectories. This preparedness reflects growing awareness that our solar system regularly receives visitors from throughout the galaxy. The statistical implications of Oumuamua's detection continue influencing estimates of interstellar object populations and their scientific accessibility. Improved understanding of detection probabilities helps plan future survey programs and mission concepts while refining predictions about discovery rates. These considerations guide resource allocation decisions and research priorities across the astronomical community. Astrobiology research programs incorporated interstellar objects into their studies of how life might spread between planetary systems. If organic compounds survive interstellar transport, these cosmic messengers could facilitate chemical evolution or even biological exchange throughout the galaxy. Understanding their compositions and survival mechanisms becomes crucial for assessing panspermia hypotheses. The legacy of Oumuamua's unusual properties extends to broader questions about the diversity of natural objects in the universe. Its extreme elongation challenged existing models of how gravitational and structural forces shape celestial bodies. This discovery reinforced the importance of maintaining open minds about what forms matter might take under different environmental conditions. Technological capabilities developed for studying interstellar visitors contribute to broader efforts in space situational awareness and planetary defense. Enhanced detection algorithms, rapid response observational protocols, and international coordination mechanisms improve our ability to monitor the space environment around Earth. These capabilities serve multiple purposes beyond pure scientific research. The inspiration provided by Oumuamua's discovery motivated new generations of scientists and engineers to pursue careers in astronomy and space exploration. University enrollment in relevant programs increased following widespread publicity about the interstellar visitor, while funding for related research attracted talented researchers from diverse backgrounds. This human capital development represents a lasting benefit of the discovery. As Oumuamua continues its eternal journey through interstellar space, it carries with it the honor of being humanity's first confirmed cosmic visitor from beyond our solar system. The brief encounter provided invaluable scientific insights while demonstrating the universe's capacity for surprise. Its legacy will endure through the expanded understanding and enhanced capabilities that resulted from studying this remarkable messenger. The story of Oumuamua ultimately reflects humanity's enduring quest to understand our place in the cosmos. Through studying this visitor from afar, we glimpsed the broader context within which our solar system exists. The discovery reinforced our connection to the galaxy while highlighting the dynamic processes that shape cosmic evolution across vast scales of space and time. In the grand narrative of astronomical discovery, Oumuamua occupies a special place as the object that opened our eyes to the regular exchange of matter between stellar systems. Its passage through our cosmic neighborhood marked the beginning of a new era in astronomy, one where we routinely sample materials from throughout our galactic environment. This remarkable messenger showed us that we are not alone in space, but part of a vast, interconnected cosmic community